Hurricane Harvey in 2017. This massive cyclone dumped 40 to 60 inches of rain across the Houston area over a 4-day period, causing catastrophic flooding and $125 billion of damage, all while the telescope was undergoing cryogenic testing at NASA's Johnson Space Center. Though the telescope remained safe inside the test chamber, water leaked through the ceilings, people had to cover workstations in plastic tarps, food was in short supply, and a few team members trapped by floodwaters had to be rescued by boat. It was rough, to say the least, but the team and the telescope survived the storm. Despite winds and snow and endless rain, the team got it done, and Webb is now ready for its final journey atop a rocket into space.
While the Webb telescope is a technological marvel, everything here began with questions. Questions about how the first stars and galaxies came to be. Questions about whether planets around other stars might have environments that can sustain life. And of course, the promise of discoveries we can't even predict yet. A few days ago, I had a chance to speak with someone who's probably the best person on Earth to help us understand what we know, what we don't know, and how Webb will help fill in those gaps. Dr. John Mather is a Nobel Prize winner observatory built here at NASA Goddard. John is Webb's senior project scientist, and we're so pleased to have you here today, John.
Good to be here with you, Michelle.
So to start this incredible story of Webb, let's start with something that's deceptively simple, gravity. There's something special about gravity.
Gravity is special. Gravity always pulls. It's the only force of nature that always pulls. So that's special. And what makes that special is that gravity, although it's very weak, is very long range. It can reach across the universe and slow down the expansion of the material that came from the Big Bang, turn it into galaxies and stars and eventually planets and a place where we could live. So that's what makes gravity special among all the forces of nature.
And something so simple, like just the idea that it's always pulling together, that simplicity leads to wonderful complexity, doesn't it?
Yes, because it's always pulling, it's possible for gravitational energy to be converted into kinetic energy, just heat, and the universe, which is not something other forces could do all by themselves. Clouds of gas can be compressed by the gravity until they get big enough and hot enough to light up and have the nuclear reactions inside that turn hydrogen and helium into the chemical elements you see around you, here in the house, here on the set. So carbon, oxygen, nitrogen, everything we have that we think of as ordinary came from inside stars. So we are stardust, as Carl Sagan told us, but there wasn't any stardust in the Big Bang. So we need this part of the story to be figured out. How did we come to be able to live here on our little planet when the universe started out without all of these goody things?
So you mentioned these planets around other stars. So we're almost sort of going through all these amazing science goals of the Webb. What can Webb tell us about planets around other stars?
Well, once in a while, a planet goes in front of the star, and some of the starlight goes through the atmosphere of the planet, if it has an atmosphere, on its way to the telescope. We will spread out that light into a spectrum, or what you would call a rainbow, and we'll analyze it to see what are the chemicals that are in that atmosphere. So we will be able to tell you that maybe, that's the plan, whether those little planets that might be like Earth actually could have, for instance, water in their atmosphere, and maybe enough water so there could be a liquid ocean under that atmosphere. One of the great questions. So we know they're planets. We know when we should look. We just don't know what we're going to see.
So after the Webb launches, one of my dreams is I'm going to be standing outside in my backyard and point to a star and say there's a planet around that star that we know has water vapor, oxygen, perhaps methane, carbon dioxide. So what is Webb going to also do in the search for life closer to home, our own backyard?
Well, here in our own solar system, we will be looking at everything from Mars on outwards to the farthest we can see. Satellites, comets, asteroids, and the planets themselves. And some of them are really interesting and special because we know they're possible homes of life. What would make a thing a home of life? Well, if it's wet. That's the good clue. So the satellite Europa, which orbits around Jupiter, was discovered by Galileo himself, and we know now that it has an ocean that's covered with ice. There are cracks in the ice where water comes spitting out. NASA are going to send a probe over there to fly through those plumes. We're also going to point over there with the Webb telescope to see what can see about that atmosphere and those plumes of water. We'll be looking at Titan, which is a satellite of Saturn, which is so big that it has an atmosphere enough to fly a helicopter. And it is cold out there, so that what they have, what is on the surface is solid ice, and over that are liquid hydrocarbons, which you home, but over there it's liquid rain, lakes of that before we send the helicopter out there.
So you're on this amazing journey from the very distant early universe all the way to our own solar system, but this has also been a personal journey for you. You've been working on Webb since the very beginning of the mission, is that correct?
I have since '95. We had our first conversation, but people were even dreaming and imagining way before that what we needed. And you could tell even before we launched the Hubble what were the possibilities, and we learned that we would need an infrared telescope that could do things that Hubble could not do.
Well, John, I've been an admirer of yours for many decades now, and it's an honor to be with you on this part of the mission. So thank you so much for joining us. Best of luck on the launch and the mission ahead.
And thank you for asking all these great questions.
The Hubble Space Telescope delivered profound insights about our place in the cosmos. But perhaps the biggest takeaway from Hubble is that we've only just scratched the surface. Hubble gave us the best ever views of stars and planets forming inside vast, dark clouds of dust. But as soon as we had that data, we were asking new questions that needed better measurements, clearer images. Hubble was also able to capture images from galaxies so far away. Their light took 13 billion years to travel to us. These distant galaxies are just tiny dots in Hubble's images, tantalizing scientists with clues about how the first galaxies formed. In order to pursue a better understanding about the earliest days of the universe, we needed to build a better time machine, and that's Webb. So I'm going to be rejoined here by Nicole and Macarena, and this is our chance to talk a bit about building that better time machine. What about the technology of Webb? So there's so many aspects of Webb to start off with, but maybe again, going back to the theme of infrared. The design of this telescope is so different because we had to use infrared light, heat light. So tell us about some of the challenges of, for example, why does it have to be so cool? Tell us about infrared light in the design.
Right. Well, I think we've heard already just how cool it has to be. It's around or below 50 Kelvin, and that's minus 370 degrees Fahrenheit. Actually, below that is what it operates at. And that's very cold. And the reason we need it so cool is because we don't want the telescope itself to detect itself because there's several instruments on board. There's 4 different instruments, and there's some moving parts, and so you need things to be cool because you want to detect these faint signatures from either an exoplanet atmosphere or faint light from the earliest stars and galaxies. So you just don't want to detect your own telescope.
Now, Macarena, you are the instrument calibration scientist for the coolest instrument.
It is the coolest
on Webb.
instrument, yes.
MIRI. So tell us a bit about MIRI and why it needs to be so cold.
So MIRI, it's a really unique instrument, and it's a great example of this collaboration we have in this mission because it's half European, half US. And so MIRI is the only instrument on board that uses the mid-infrared light. And the mid-infrared light is a bit redder, a bit cooler than the near-infrared light, and so because of that, MIRI needs to be colder in order to detect that very faint signal from high-received galaxies or protoplanetary disks, etc. So because of that, it's the only instrument on board that has a cryocooler. So it is not only the passive cooling from the sun shield, it is active cooling, and it brings it down to about minus 450 Fahrenheit. So it's really extremely cold, a few degrees above the absolute zero.
And we were talking about you don't want the telescope to be so hot that it's basically giving off its own signal, its own radiation, and that leads us to why it needs to be in space, right? So tell us a bit about why do we need to launch this thing into space to see these wavelengths?
Well, again, it kind of goes back to atmospheres because Earth has an atmosphere and there's water in Earth's atmosphere as one example. I mean, there's basically in the infrared at the wavelengths that we want to observe some of these stars and planets and galaxies. Those wavelengths are actually where Earth's atmosphere is opaque. So with telescopes located on Earth, even at higher mountains where they try to get above the clouds or atmosphere sometimes, there's still residual atmosphere that we're trying to look through and peer through. So in order to see the full infrared wavelength range at a very high sensitivity as well, we need to go to space.
Absolutely. So we talked a bit about some of the power of techniques like spectroscopy. We've heard Dr. John Mather talk about it. So let's go a little bit more into the details of how spectroscopy works and why it's so powerful. Continue.
Oh, sure, yeah, I can keep going. Well, with spectroscopy, we heard, so visible light, again, is kind of, it's a rainbow of colors that we don't see naturally. But if you use something like a prism, you can separate out that light and see all the colors from, blue to red. But then the infrared is redder than the human eyes can see. But you can still do the same technique where you have spectroscopy tools or instruments like Webb has, all these spectroscopic tools, so that we can break up the infrared light and look at certain colors, if you will, so that we can see certain features that we are looking for, whether it's the right wavelength where, a galaxy might be bright or where water is absorbing in an atmosphere.
So, Macarena, MIRI has many different capabilities.
It does.
And in fact, it has one that I believe is it's something different called coronography as well.
Yes.
Tell us a bit about all these ways that we're going to detect different signatures from planets. Tell us
So
about MIRI.
coronography, it's an amazing technique, but essentially it simulates an eclipse. So when we have a very bright star with planets around, for instance, usually when you take an image, the stars outshines the light of the planet, so you don't see them. But with MIRI and with other instrument NIRCam as well, you can actually block the light of the star and dim it, and then you see the planets around. And it's really a technique that's going to be very much used and to do, like in this image, direct imaging of planet.
Well, thank you so much. We'll be back to talk to you more with some social media questions. Thank you very much.
Thank you.
NASA and its partners began developing the Webb telescope years ago, growing from an initial inspiration to a design, then schematics, and finally, reality. What started as a big dream of studying the origins of the universe required best-in-class engineering expertise to transform into something real. Let's take a short look at the very long story about the earliest days of the James Webb Space Telescope.
Before the Hubble Space Telescope even launched, scientists were already discussing what should come next. Ideas for what was then called the Next Generation Space Telescope evolved throughout the 1990s, and by the end of the decade, NASA had a preliminary plan. Construction of the James Webb Space Telescope began in 2004. Beryllium was mined to create the mirror segments, which technicians polished and coated in a thin layer of gold. Meanwhile, engineers designed and built new science instruments in the US, Europe, and Canada. Every step of the way, there were reviews and tests to make sure each part could withstand the rigors of spaceflight. By the early 2010s, the team began bringing individual components together at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It was there that the mirrors and instruments began to coalesce into the grand machine we see today.
We've said before that the James Webb Space Telescope is an incredibly ambitious mission. Big ambitions come with big challenges, and that's certainly been the story of Webb. From the beginning, the design of this observatory has been a balance between the boldest questions scientists have dared to ask and the cutting-edge technology that our best engineers could offer. The design for Webb evolved from earlier ideas of what a telescope could be, another example of the delicate balance between desire versus capability. To get a better understanding not only of the mission's goals, but also the mechanical guts of the observatory, I speak with a pair of engineers who know the anatomy of the Webb telescope better than just about anyone. I'm here with Keith Parrish, a senior engineer on the Webb mission. And Keith, you brought something to show us today.
Yeah, yes, I did. So conceptually, Webb Sunshield is actually quite simple. All we need is 5 tennis court size pieces of this material outstretched to protect the telescope from the sun. So what I have here is an actual sample of that material. This is just Kapton.
It's so light, yeah.
Yeah, it's an industrial, you can buy this and it's commonly used. And what we do is we buy it for Webb. We seam it all together in small pieces and then we actually coat it with special coatings to give it the what we call the thermal properties we need in orbit. So this one has a nice pink or purplish kind of hue to it, and the reason it's purplish in hue, we use this on the sun side, and we actually put a silicon material on this Kapton, and then we actually put a little bit of a metal in it, and what that metal does is it gives us a nice electrical conductivity. We don't want any surface charging building up, and the other thing is this silicon of this layer. So, and also it's very durable and can survive, for many, many years in space.
And then this whole thing has to unfold somehow, where we can actually see that behind us.
Exactly right. So if you look at that animation there, unfolding there, so it's actually S-folded up. almost like a fan. We call it